I am delighted to present our next presenter, Dr. Oliver Myers. What a fitting case for us. He is an M1. An M1. Give him a round of applause. Dr. Myers is currently at Northrop Grumman, and we are delighted also that he is also an adjunct faculty member in mechanical engineering, teaching a 60-student capsule design course. So thank you, Oliver. So today he's going to present modeling piezoelectric thin films microactuators.
Good morning. As Dr. Harlan Beatties mentioned, my name is Oliver Myers, and I'm an M1. I will be presenting some of my work in terms of modeling piezoelectric thin-film microactuators. I'm a senior design engineer at the Northrop Grumman Electronic Systems right beside BWI Airport. Microelectromechanical systems using smart materials have been investigated for microactuators and microsensors, specifically because they can convert energy with low input power and develop high outputs, as an example, either deflections or strains. Piezoelectric materials in particular exhibit a coupling of mechanical behaviors. Applying a mechanical load generates an electric field, and the inverse, applying an electric field, generates mechanical stresses and strains. And in this case, you've seen a lot of materials or a lot of devices that use piezoelectric materials. For instance, if any of you have your cell phones on, please turn them to vibrate and you will feel the usage of piezoelectric materials. My wife actually enjoyed this picture because she has a career in singing, and she actually noticed that, or did not notice that piezoelectric materials were used to generate the harmonics and vibrations that she uses to sing to generate the voices over the loudspeakers, which are shown here. And if anybody has these in their cars, you have a large piezoelectric disc, and you're about to blow your eardrums out. But in this case, I'm using microactuators or piezoelectric materials for microfluidic applications based on transport phenomena. If you look at the picture to your far left, this is an example of one of the devices that was established for my body of research. And the applications can range from micro fuel delivery systems. We have a small aircraft that's used to detect what you're doing. So if you see a little bug flying around here, you're under surveillance at this point now. Also, in coupling with some of the research that was previously mentioned, we could use microfluidics to actually transport proteins. Who was the protein presenter earlier? And drug delivery. However, for military applications, currently there is a chem-biological detection sensor that is a two-man operation. And if anybody has been in the military or been on a forced march with a 30-pound pack, you only can make about a couple of miles at a time. So what if we were able to use this system to integrate into something the size of a BlackBerry, or the next generation to something the size of a watch, so you can actually detect what chemicals are going on here in this room, for instance. If we had any mustard gas or VX poison gas here in this room, you would be able to detect it just by opening your BlackBerry and putting a sample into the pump system and saying, okay, we have to get out of here right now. So our motivation was to actually help Northrop Grumman and help Penn State in their design and fabrication process, because it takes a lot of time to design, analyze, fabricate, and conduct experiments, and it's very costly, very repetitive, and very time-consuming. So Penn State and Northrop Grumman finally wised up and incorporated UMBC and brought us in, as the geniuses that we are, to develop cost analysis tools to predict the actual multifunctional capabilities of piezoelectric MEMS devices. Yes, this looks like a hodgepodge of equations, but these are actually the fundamental equations for deflection, W, with a uniformly distributed load over the radius of an actual circular disk. The extension of that is when we apply multi-material conditions or equivalence Young's moduli and Poisson's ratios based upon weighted ratios of the various materials used in the actual diaphragms. Coupling the piezoelectric theory, you see that we have coupling with electrical and mechanical loads. So we have to incorporate a lot of linear algebra to incorporate these properties and these materials into the deflection models. Numerical models were then generated using a finite element-based program that we incorporated a lot of the material conditions, the thicknesses, the various Young's modulus, Poisson's ratio, and densities into a 3D model using symmetry. And here is an example of the actual model that we used. And here I incorporated the actual piezoelectric coupling, stiffness matrices, and permittivity coefficients, or the key properties of the piezoelectric material. This just shows the actual boundary conditions used, or simulated boundary conditions, where a simulated force was applied in the downward direction, and the red indicates the clamping or the force boundary conditions. In this case, this is not an actual force. However, this is an actually applied voltage to generate the deflection that we wanted to use or wanted to obtain. This is some of the results from the numerical model, where we used what we call a planar capacitor model, which is simply a disk, several layers of material with electrodes that surround the piezoelectric material. And we get a deflection of about 15/10 of a micron, with a maximum stress, of course, at the clamp boundary conditions. Now, the limitations of our models is that the analytical models aggressively predict and then conservatively predict the actual deflection, versus the numerical models are a little more accurate in terms of their deflection parameters. Again, the first sample planar capacitor, I was able to show that the stresses are focused at the very clamped end, and also there's a range of stresses that are generated just by varying the piezoelectric thickness in the actual materials. From that same exact model, without changing any of the boundary conditions, without changing any of the equations or anything, I was able to actually develop and extract the harmonics and the deflection of those harmonics. And you see the first, third, and the fifth are actually symmetric harmonics, while the second, fourth, and sixth are non-symmetric. A second device was made with different electrodes. Here we use platinum, 1.6 microns of piezoelectric material, and a protective layer of silicon dioxide. And this generated the maximum deflection of 2.3 microns, closer to the desired deflection that we wanted in these devices. And again, from that same model, I was able to extract the harmonic resonance and the harmonic data for those devices. And these actual harmonic data compares very well in the third and fourth frequencies. However, it's very conservative in the first and second. As a sub-conclusion, these models compared very favorably with the initial data and established literature. The models will be implemented and are currently being implemented and upgraded to improve the actuator designs. These models were made using 3D and 2D axisymmetric models with multi-material conditions and coupling the piezoelectric material properties. For what we call an interdigitated electrode or interdigitated diaphragm, where the actual electrodes are now on top of the piezoelectric material versus integrated into the diaphragm. Again, we use an extra material for the electrodes, which is gold. So if anybody has any jewelry, I could melt it down right now, and I could take that and make some more devices. We're short on money, so any extra gold jewelry that you have, I'll be glad to take from you. You're laughing. I'm serious. Okay. Because of the actual processing conditions, we had to incorporate additional residual stresses that are actually internal to the piezoelectric and to the host materials into the diaphragms. These charts actually showed some of the deflection profiles and a summarization of the actual deflections, maximum deflections at various thicknesses of piezoelectric material. One of the things that we also have to consider are the design parameters of these particular devices. Now, with the planar devices, the only design parameter was the thickness. But with the interdigitated devices, we had to include design parameters of electrodes, electrode width, electrode pitch, the center disk diameter. And you can see that there is a 10% variance between an even number or odd number of electrodes. An even number of electrodes also simulates that it's a closed circuit. An odd number of electrodes simulate that it's an open circuit. So we get a better response with an even number of electrodes. some of the boundary conditions, and now this may seem simplistic, however, when you're actually fabricating these devices, you actually have very little control in how your boundary conditions are set, because you're actually using ions to separate the material from the actual host material. So you actually don't know whether or not you're getting a fully clamped boundary condition here, if it's partially clamped here, or if it's fully clamped farther in. And this just shows some of the actual deflection comparisons, if you will, from the various boundary conditions that were modeled. So in a brief summary, the interdigitated became more complicated because of the incorporation of the multi-material conditions, because of the piezoelectric company, and because of the various design parameters. And there was some work that was done to actually help optimize the design based upon material conditions, material thicknesses, center disk diameter, and even voltage polarity, whether or not to use the outer electrodes as the positive or the outer electrodes as the ground. And a lot of these models actually show the effects and the design parameters of the couplings and combinations on deflection. In terms of experimentation, here's one of our little devices. And actually, and I say littles because it's a lot smaller than the hairs on my head. And no, I don't have any hair, so it's probably a lot larger than the hairs on my head now. But this is one of the actual designs that we used. And as I mentioned before, we had to use the design parameter of the polarity on the inner or outer electrodes. And these just show some of the scanning electron micrographs of these devices. And this is the actual exploded view of a micrograph picture. This is our experimental setup. We used a zygo interferometer to actually calculate or extract the static deflection of these devices using a simple voltage generator. 140 volts was applied. That may seem like a lot, but if you're using a DC voltage at very low current, it's basically what you're using on your watch. These scans actually show the comparison of the experimental profiles, which seem very conical, in comparison to the numerical profiles, which are very parabolic. One of the extensions of the research that we have to do is to determine whether or not or why this actually occurs at the clamped end, where we have a first resonance deflection or positive resonance deflection. We also have to determine why the shape functions are not very well corresponding. Initial presumptions are due to the residual stress and to the clamping conditions that we have in the actual models. And this also shows another comparison where we've actually reversed the polarization. And again, you get a much larger resonance deflection at the clamped end. This just shows a sampling of some of the deflection comparisons where we have positive polarity on the outside and a positive polarity on the inside. The positive on the outside seems to indicate that we get a much larger deflection versus the positive polarity on the inside, except for this one who wants to be an oddball. And we have to continue to work on that type of experimental data. So our experiments were used to determine the maximum deflections of the diaphragms at the center of the disk, and it partially captured the stair-step deflection, if you will, identified some of the effects on the residual stresses of the deflection, initial verification that an even number of electrodes gives us a much larger deflection, and identified the deflection with the difference with respect to the polarity. And in conclusion, this body of work actually combined several areas of mechanics of materials, smart materials, finite element modeling, which is Dr. Harlan Beatty's specialty, experimentation, which is actually fun because I get to play in the laboratory, and concludes with my full body of research for this particular area for a microfluidic application. Thank you very much. That is actually going to be an extension of my work. PZT, in this case, was the host material that we chose because of its coupling coefficients. In particular, it was PZT5H. Some of the other material I like to investigate are magnetostrictive materials or shape memory alloys.
Any other questions? Yes,
So you plan on integrating these with the micro valves and micro pumps, or is the end application?
The end application is the actual specific application is the micro valves and micro pumps. But the end application can be anything from drug transfer to fuel delivery or the chemobiological fluid detection systems.
But we will stop it there for the interest of time. So thank you very much.
Thank you.